Hello, my name is Nicole PIEDRAHITA. I'm from the University of Washington, and my research topic is about optimizing the thermomechanical performance in the vanadium HEAs with molecular dynamics. I'm sponsored by the online REU program, and I'd like to acknowledge my mentors Jacob Start and Sariu Fenson, who have helped me learn the methods for this research project. Advancing technologies for high temperature and high stress environments depends on the development of high strength alloys. Developing these alloys is incredibly important for high temperature applications in many industries, including aerospace and nuclear energy. Regular alloys don't have the same properties as high entropy alloys, or HEAs, so at high temperatures, regular alloys and metals are softer. What makes HEAs distinct are their 5 near equimolar elemental compositions, which allow them to stay strong at high temperatures. Additionally, refractory high-entropy alloys are a subgroup of HEAs that have higher melting temperatures. Our alloy of interest is a rHEA that exhibited high structural stability and mechanical resilience under high temperature and dynamic loading conditions in past investigations. On the right is an example of how yield strength is maintained by 2 HEAs in a 2011 experiment. Our alloy, though, possesses a large and complex compositional design space, which makes it costly and time-consuming to search for optimal alloy compositions. So instead of using a physical experiment with a traditional trial and error process, computer modeling makes the task much more efficient. The main goal is to optimize HEA properties. This will be done by searching the composition design space using the formula AX BCDE 1 - X. This ensures that the HEA alloy composition is near equimolar, even though it still has a dominant element characterized by the letter A. So we will have simulation runs where vanadium, niobium, tantalum, titanium, and zirconium take turns being dominant elements. The compositions of the dominant elements start from 0.05%, increasing by 0.05 up until 0.3%. 0.5% is the greatest composition percentage tested and deviates from the 0.05 increase. By changing the compositions like this, we hope to increase the bulk, shear, and elastic moduli and decrease the thermal expansion to make the overall alloy stiffer. A stiffer alloy would resist compression, deformation, bending, and volume changes in high temperatures. The alloy was simulated using molecular dynamics simulations. The first calculations done were the lattice constants. They were used for the thermal expansion calculations in the formula L minus L naught over T minus T naught times 1 over L naught, where L naught is the lattice constant and L is the change in the length of the simulation box. 2 simulations were run to calculate thermal expansion. One was at 1000 Kelvin and the other was at 300 Kelvin. The temperatures were held constant for 50 picoseconds. The volume of the simulation box changed based on the temperature in both simulations, so the difference in volume was calculated. For the elastic properties, the bulk modulus was calculated using small strings that were applied to the unit cell, shearing it in different ways. Every time it was sheared, the energy was calculated. The relationship between stress and strain, depicted in tensor form on the right, was used to calculate the elastic constant matrix. The elastic constants seen in the matrix on the right were averaged out, and those averages were used to calculate the bulk and shear moduli and Poisson's ratio. Afterwards, the elastic moduli for each element were calculated using Poisson's ratio and shear moduli. Each element's composition was adjusted using the ABCDE formula mentioned earlier, where A is represented by the dominant element. During each run, the alloy had varying dominant concentrations. When the zirconium composition increased, the lattice constant increased. This data is important for later properties calculations because the whole alloy reflects the behavior of individual elements. When comparing thermal expansions, vanadium actually decreases the thermal expansion as its concentration increases. The opposite can be said for titanium and zirconium. This can be explained by their lattice structures. Vanadium, niobium, and tantalum are BCC metals, while titanium and zirconium are hexagonally packed, or HCP. The entire alloy we're making is overall BCC, so when adding HCP elements like zirconium, this disrupts the phase stability, which tends to increase thermal expansion. To make an alloy that resists changes to its volume during high temperatures, it would need to have more vanadium in its composition to make the thermal expansion smaller. Straining the unit cell in different ways with varying compositions in the simulation runs resulted in the bulk modulus being higher when tantalum and zirconium had higher concentrations. The phase stability of the alloy is stronger because the bonds in these two elements are stiffer, which explains the increase in the bulk modulus. So this means that if we want an alloy that resists compression, tantalum and zirconium should dominate the composition. Just like in the bulk modulus plot, zirconium increases the shear modulus as its composition increases, so it makes the alloy more resistant to shear deformation. Here, the elastic modulus increased when more zirconium was added. This makes the alloy more resistant to bending and stretching. Before moving on, I'd like to point out some things. HEAs are known for being near equimolar, so their element compositions are relatively uniform. During the simulation runs, it's notable that the compositions become non-uniform. For example, when vanadium had a percentage of 0.5, the other elements during that simulation run were at 0.125%. The more an element becomes dominant, the less HEA properties are exhibited. This was more apparent during the thermal expansion runs, where more uniform compositions had lower thermal expansions. Another thing to keep in mind is that the atoms are randomly ordered in an HEA. With billions of atoms randomly oriented in a real HEA alloy, this simulation just shows a finite representation of that, so it may not fully show the extent of real-life HEA behavior. Seeing how an increase in vanadium increases the alloy's resistance to volume changes in higher temperatures, and how increasing zirconium makes the alloy stiffer, it opens the door to exploring the compositional design space. In future experiments, the database of material properties and compositions that were made can be fed into a code that will predict new HEA compositions to optimize all the material properties. A new alloy composition would then be put into lamps, where new material properties would be calculated and the Bayesian optimization algorithm would update its predictions and provide new compositions to test. Future experiments like these would help create high entropy alloys for high temperature applications. Thank you for listening.